Hello. Thus far we have been talking mainly about the electronic problem. But what about the equations of motion for the nuclei? Well, if we take a diatomic molecule, the first order approximation for a diatomic molecule is a simple harmonic oscillator, that is a pair of balls connected by a spring, as shown here. The potential energy is given by this parabolic potential with the equation V of r equals half k, k being the force constant, times r minus r0 whole square, where r is the internuclear separation and r0 is the equilibrium internuclear separation. A better approximation, of course, would be the Morse potential. The eigenfunctions of the quantum harmonic oscillator are related to the Hermite polynomials, which take this form, and the solutions are shown here with the eigenvalues En equals n plus half h nu. That is, the energy levels are equally spaced. Compare this with a particle in a box where the energy is proportional to the square of the quantum number. That is, the energy levels get farther apart with increasing n. Assuming that the internal vibrational motions in a general polyatomic molecule can be represented as a set of uncoupled harmonic oscillators. So for each bond, we can write a harmonic oscillator potential of this form. Now note that the negative gradient of the potential is the force, and the second derivative is the force constant, that is del 2 V alpha by del R alpha squared equals K alpha, the force constant. So we get the vibration frequency nu equals 1 upon 2 pi root K by mu, where mu is the reduced mass m1 m2 by m1 plus m2. The expression for the quantum mechanical force in a molecule is given by the Hellman-Feynman theorem. Now the electronic energy and the electron nuclear repulsion form the potential energy surface upon which the nuclei move. Now the electronic Hamiltonian is given by this expression, and we note here that the only term which depends upon the nuclear coordinates r alpha is this term, which is the electron nuclear Coulombic attraction term, and therefore the gradient of the electronic Hamiltonian with respect to the nuclear coordinates, that is del alpha He, is just del alpha Vne. Now the expectation value of the electronic Hamiltonian is the electronic energy E. Therefore, the gradient of the electronic energy with respect to the nuclear coordinates, that is del alpha E, is given by differentiating this equation by parts with respect to r alpha, and that gives the differential of the bra times this plus the differential of the electronic Hamiltonian, which gives this term, plus the differential of the ket times this. And therefore, but here we note that the sum of the first term and the third term is just bra del alpha He psi ket plus bra He psi del alpha psi ket. In here we have used the Hermitian property of the electronic Hamiltonian to go from this expression to this expression. But that is just E times bra del alpha psi ket plus E times bra psi del alpha psi ket, where we have used the eigenvalue property of the Hamiltonian, that is He psi equals E psi in both the ket and in the bra to get this expression. But that is just E times bra del alpha psi ket plus bra psi del alpha psi ket, or in other words, E times del alpha of bra psi ket. But bra psi ket is just a normalization, and its derivative is equal to 0, or in other words, the first and third terms in this expression for del alpha E cancel out, and therefore that gives us the expression for the Hellman-Feynman force F alpha is equal to minus del alpha E, which is equal to the negative of the expectation value of del alpha V and E. So the Hellman-Feynman force on nucleus alpha is F alpha equals minus bra psi del alpha V and E psi ket. And the total force on nucleus alpha is thus the Hellman-Feynman force minus del alpha V and N, that is the gradient of the internuclear repulsion. This force is a vector in 3n minus 6 dimensional space, 3n minus 5 for a linear molecule, because the electronic energy does not depend upon the 3 translational coordinates and the center of mass rotation. And it has a component of this force along each normal mode of vibration. This leads to a generalization of the Hellman-Feynman theorem, where the electronic Hamiltonian He depends on some parameter zeta. We can generalize the Hellman-Feynman theorem and derive the expression in the same way as del E by del zeta equals bra psi del He by del zeta psi ket. The Hessian matrix is the matrix of second derivatives of the electronic Hamiltonian with respect to the nuclear coordinates. It is a tensor, a matrix with 3n rows and 3n columns. The eigenvalues of the Hessian are related to the normal mode frequencies. These are the diagonal elements of the Hessian matrix. The corresponding eigenfunctions are the normal modes of vibration. The transition probability from initial state psi I to final state psi f is, to first order in perturbation theory, proportional to the square of the matrix element of the perturbation, or the interaction Hamiltonian between matter and radiation, that is H dash equals P dot A, between the initial and final states, that is bra psi f H dash psi I ket modulus squared, which appears here. This is known as Fermi's golden rule, which was actually first derived by Paul Dirac in 1927. Whether light can induce a transition from initial state psi I to final state psi f depends upon whether this transition integral is non-zero. The selection rules for vibrational spectroscopy in the harmonic approximation are delta nu equals plus minus 1, that is, transition only between adjacent vibrational levels. For a vibrational mode in a sample to be infrared active, it must lead to a change in the dipole moment of the molecule. If we include anharmonic corrections, as in the Morse potential, this modifies the selection rules to delta nu equals plus minus 1, plus minus 2, plus minus 3, etc. For the quantum rigid rotor in field-free space, the Hamiltonian is simply the kinetic energy operator, that is H equals minus h cross squared by 2 mu del squared. In spherical polar coordinates, this takes the form H equals minus h cross squared by 2I into 1 upon sine theta del del theta of sine theta del del theta plus 1 upon sine squared theta del squared by del phi squared, where I is the moment of inertia, I equals mu r squared. The eigenfunctions of the quantum rigid rotor are spherical harmonics yjm of theta phi with eigenvalues E equals bj into j plus 1, where b equal to h cross squared by 2I. The selection rules for pure rotational spectra are thus delta j equals plus minus 1. Rotational transitions can happen along with vibrational transitions, leading to rho vibrational spectra. Here is the schematic energy level diagram for a linear molecule. This is the ground vibrational level V equal to 0, and this is the first excited vibrational level V equal to 1. Transitions can happen from different rotational levels of the V equal to 0 vibrational level to different rotational levels of the V equal to 1 vibrational level. Transitions with delta J equals minus 1 are known as the P branch, and transitions with delta J equals plus 1 are known as the R branch. transitions with delta J equal to 0 are known as the Q branch, and they are forbidden. So this leads to the spectra here for carbon monoxide. This is the P branch at lower energies, and this is the R branch at higher energies, and there is a gap here which corresponds to the missing Q branch. Similarly, we see here the simulated spectrum of the carbon-chlorine stretching band in methyl chloride. Let us now return to the harmonic oscillator, whose Hamiltonian is H equals P squared by 2 mu plus half kx squared. We introduce the dimensionless variable, which I shall call tadpole, which is equal to square root of mu omega by h cross times x, where omega is square root of k by mu. In terms of this dimensionless variable, then P equals minus I times square root of mu omega h cross dd tadpole, and x equals square root of h cross by mu omega times tadpole. And then the Schrödinger equation in terms of this dimensionless variable becomes half h cross omega times minus d squared by d tadpole squared plus tadpole squared operating on phi of tadpole equals E times phi of tadpole. We now introduce the Fock operator A equals square root of half times dd tadpole plus tadpole, and its Hermitian conjugate A dagger equals square root of half times minus dd tadpole plus tadpole, in terms of which the momentum turns out as P equals I times square root of mu h cross omega times A dagger minus A, and the coordinate as x equals square root of h cross by 2 mu omega A dagger plus A. The commutation relation for the Fock operator and its Hermitian conjugate then gives commutator of A and A dagger equal to 1, from which the Heisenberg relation follows that the commutator of P and X is equal to h cross by I times the commutator of A and A dagger, which is equal to h cross by I. Substituting these expressions for P and X in the equation for the Hamiltonian, h equals P squared by 2 mu plus half kx squared gives h equals half h cross omega times A dagger A plus A dagger, and that, if we use the commutation relation between A and A dagger equal to 1, gives half h cross omega times 2 A dagger A plus 1. Thus, in terms of the Fock operator, the Hamiltonian takes the simple form h equals h cross omega times A dagger A plus half. A dagger A is the number operator, and in the case of a periodic solid, which can be treated as a collection of harmonic oscillators, A dagger A is the number operator for phonons. We now introduce the dimensionless Hamiltonian operator 1 upon h cross omega times h, which is equal to a half times minus d squared by d tadpole squared plus tadpole squared, which is equal to A dagger A plus half, and the dimensionless energy epsilon equals E by h cross omega, which gives the Schrödinger equation as small h operating on phi equals epsilon phi. Then the commutator of small h and A dagger is equal to the commutator of A dagger A and A dagger, which is equal to A dagger A dagger minus A dagger A, which is equal to A dagger times the commutator of A and A dagger, and using the value of that commutator, that is equal to A dagger. Thus, small h times A dagger operating on phi equals A dagger plus A dagger small h operating on phi, which is equal to epsilon plus 1 times A dagger phi. Thus, if phi is an eigenvalue of small h with eigenvalue epsilon, then A dagger phi is also an eigenfunction of small h but with eigenvalue epsilon plus 1, and A phi is also an eigenfunction of small h but with eigenvalue epsilon minus 1. So what A dagger does is that it increases the eigenvalue of small h by plus 1, and what A does is that it decreases the eigenvalue of small h by 1. Then by induction, similarly, we get the commutator of h and a dagger to the power n is equal to n times a dagger to the power n, from which it follows that small h times a dagger to the power n operating on phi is equal to epsilon plus n times a dagger to the power n operating on phi. And likewise, it can be shown that the commutator of small h and a to the power n equals minus n times a to the power n, from which we get h times a to the power n operating on phi equals epsilon minus n times a to the power n operating on phi. Thus, we have seen that a dagger raises the eigenvalue of small h by 1 and is therefore called a creation operator, while a lowers the eigenvalue of small h by 1 and is thus called an annihilation operator. Let us call the lowest energy eigenstate by phi 0 and successively higher energy eigenstates as phi 1 equals a dagger operating on phi 0, a2 equals a dagger squared operating on phi 0, phi 3 equals a dagger cubed operating on phi 0, etc. until phi n equals a dagger to the power n operating on phi 0. Then it can be shown that a has to annihilate the lowest eigenstate, that is a operating on phi 0 gives 0. Then small h operating on phi n equals a dagger a plus half operating on phi n, which is equal to n plus half times phi n, the solution of the harmonic oscillator that we have already encountered. Thus, this leads to the identification of a dagger a as a number operator, since it gives the number of quanta as the eigenvalue. That is, a dagger a operating on phi n gives n times phi n. Then operating with small h on the lowest eigenstate phi 0 gives a dagger a plus half operating on phi 0, which is equal to half phi 0, since a dagger a operating on phi 0 has to give 0. Or this shows that epsilon 0, the 0 point energy, is equal to a half in units of h nu or h cross omega. If there are oscillators of different frequencies, that is different phonon modes labeled as k, l, etc., then we can write the commutation relations for bosons as commutator of ak and al dagger equal to delta kl, which is equal to 1 if k equal to l and 0 if k not equal to l. Commutator of ak and al equal to 0, that is the annihilation operators for different phonon modes commute, and commutator of ak dagger and al dagger equal to 0, that is the creation operators for different phonon modes commute. The number operator for any mode k can have eigenvalues nk equals 0, 1, 2, 3, 4, etc. That is any positive integer eigenvalue. These considerations may be used to construct a quantized formulation of the electromagnetic radiation field by treating it as a set of discrete oscillators whose excitations are photons. As we have seen in an earlier episode, the Hamiltonian for the electromagnetic field in free space, that is in the absence of charges and currents, is given by h equals half integral d tau e squared plus b squared. The quantized vector potential is then given in terms of the creation and annihilation operators by this expression, where k is the direction of propagation of the beam and the summation is over the two transverse polarization directions perpendicular to it, and capital N is the normalization constant. The electric field is then given by E equals minus del A by del T, with the scalar potential phi being equal to 0, and that is obtained by differentiating this equation for the vector potential with respect to time to give this equation here. Likewise, the magnetic field B is equal to del dot A is obtained by differentiating the expression for the vector potential with respect to the space coordinates to give this equation. The point to note here is that the electric field is in the same direction as the vector potential, whereas the magnetic field is normal to it. Substituting the expressions we obtain for the electric and magnetic fields in the equation for the Hamiltonian, H equals half integral d tau E squared plus B squared gives H equals integral dk H cross Ck sigma sigma Ak sigma dagger Ak sigma. The number operator for photons is n equals integral dk sigma sigma Ak sigma dagger Ak sigma. The zero photon state phi 0 is known as the vacuum state. Okay, all that was for bosons. What about fermions? Fermion creation and annihilation operators anti-commute. That is, anti-commutator of Ck and Cl dagger is equal to Ck Cl dagger plus Cl dagger Ck, which is equal to delta Kl, which is equal to 1 if K equal to L and equal to 0 if K not equal to L. And likewise, anti-commutator of Ck and Cl is equal to Ck Cl plus Cl Ck equal to 0, and anti-commutator of Ck dagger Cl dagger is equal to Ck dagger Cl dagger plus Cl dagger Ck dagger is equal to 0. This last relation ensures that we cannot create a state with two fermions in the same set of quantum numbers, and this is the Pauli exclusion principle. That is, Ck dagger Ck dagger is equal to 0. The only allowed eigenvalues of the fermion number operator are now nk equal to 0 or 1 for any k. For a periodic solid, as we saw in the previous episode, the Hartree-Fock ground state phi 0 is the state where the lowest n by 2 energy levels, that is called the valence band in a metal, are filled, and all the higher energy levels, that is the conduction band, are empty. That is, phi 0 is the single determinant psi a alpha, psi a beta, psi b alpha, psi b beta until psi half n alpha, psi half n beta. Excitation of an electron from the valence band to the conduction band corresponds to the creation of a positively charged hole in the valence band and simultaneous creation of an electron in the conduction band. Thus, we create a hole in the valence band and an electron in the conduction band by promoting an electron from the level I in the valence band to the level M in the conduction band. Such an electron-hole pair is known as an exciton and is represented by a diagram like this, where the electron lines are directed upwards and hole lines are directed downwards. The Hartree-Fock ground state phi 0 is the zero exciton state. Okay. We will talk more about excitons in the next episode, but we will first introduce the Feynman diagrams and talk about quantum electrodynamics also. Okay. See you next time.